So we're starting section 5.7, solving recurrence relations by iteration. So I'm going to start the section by saying that it is often helpful to have an explicit formula for a sequence instead of a recurrence relation. Just think about our application problem from the last section. We had to do 21 computations to answer the question, and it would be nice if we didn't have to do all those computations. So, such an explicit formula is called a solution to the recurrence relation. So the question becomes, how do we find a solution? To a recurrence relation. And the answer to that question is that we're going to use a method called the method of iteration. So let me explain briefly what iteration is. So you're going to start with the initial conditions that you're given in a recurrence relation. And then what you're going to do is you're going to calculate successive terms of the sequence until you see a pattern. Basically, what you're trying to do is come up with a formula for something. And so in order to do that, you have to observe or notice a pattern. Formulas are based off of patterns. So let's look at an example here. Let's say I'm looking at a sequence, A0, A1, A2, be the sequence defined recursively as follows. So for each integer k greater than or equal to 1, I'm going to say that ak is ak minus 1 plus 2, and a0 will be 1. My initial term will be 1. And I want you to use iteration to guess an explicit formula for the sequence. All right, so we're going to use our method of iteration, start with our initial condition. A0 was 1, and A1 would be 1 plus 2. Or 3. A2 would be 3 plus 2, or 5. A3 would be 5 plus 2, which is 7. And so forth. So maybe you can notice a pattern. It's nice to think about these kind of in the following way. So let's rethink about this a little bit. A0 was 1. A1 was 1 plus 2. A2, you take your previous result, 1 plus 2, and then you add 2 to that. A3, take your previous 1 plus 2 plus 2 plus 2. And then you'll notice this kind of pattern that you see. You always have 1, 1. So, and then the number of 2's goes up. So let's look at this. Let's say A0 was 1 and it had no 2's, 2 times 0. A1, it was 1 plus we had 1 2. A2, 1 plus we had 2 2's, so 2 times 2. A3, 1 plus we had 3 2's, so 2 times 3. And hopefully from here you can kind of see a pattern emerging. So we can guess our formula would be AN would be 1 plus 2 times n. So this type of sequence is very special. It's called an arithmetic sequence. And arithmetic sequences, you can write them as AK equals AK minus 1 plus D for each integer k greater than or equal to 1, where D is a constant. So in our example, D was 2, and you can always write the solution of an arithmetic sequence. It'll have this nice formula. AN will be A0 plus D times N. So if you compare this with your example, you'll see that it follows the same format. A0 was 1, D was 2. So if you plug those in, you get the same answer we got in our previous example.